Simple functions are often put together to make more sophisticated structures. Two functions can be composed by nesting one function within the other. The chain rule we derived in the previous video helps us to calculate the derivatives of functions put together in this way. Another way to put two functions together is to write down their expressions next to each other so as to obtain their product. The purpose of this video is to derive the product rule, which is used to calculate derivatives in such situations. A on x is the product of f on x and g on x. We want to calculate the derivative dA dx at x equals x naught, which is the limit as delta x approaches 0 of the numerator a on x naught plus delta x minus a on x naught divided by denominator delta x. We plot f on x versus x in the horizontal plane. The x-axis points toward the viewer and the f on x, that's to say the y-axis, points to the right, slightly toward the viewer. We plot g on x versus x in a vertical plane. At x equals x naught, the values of g on x naught and f on x naught are the lengths of the sides of a rectangle whose area is a on x naught. Walking away from x naught and toward the viewer, we draw the rectangle at x equals x naught plus delta x, whose area f on x naught plus delta x times g on x naught plus delta x is a on x naught plus delta x. The difference between the areas of these two rectangles, a on x naught plus delta x minus a on x naught, is the total area illustrated in the light blue, green, and magenta rectangles. When we consider a limiting process in which delta x becomes arbitrarily small, we consider a process in which the light blue, green, and magenta rectangles become arbitrarily small. The light blue and magenta rectangles shrink only in either the vertical or horizontal direction, while the green rectangle shrinks in both the vertical and horizontal directions. As delta x becomes small, the green area is said in vernacular English to be doubly small and thus negligible in comparison to the blue and magenta areas for the purposes of determining delta A. Delta A is therefore approximately just the area of the magenta rectangle, which has width f on x naught plus delta x minus f on x naught and height g on x naught, plus the area of the light blue rectangle, which has width f on x naught and height g on x naught plus delta x minus g on x naught. Divide everything by delta x. We have allowed delta x to be small, and we will now assert that we are considering the situation in which the functions f and g have nice smooth plots, without weird jiggles or jagged corners. Given these conditions, we anticipate that we approximate derivatives when we calculate ratios of differences obtained by using x values separated by small finite distances. Thus, dA dx at x equals x naught equals df dx at x equals x naught times g on x naught plus f on x naught times dg dx at x equals x naught. This is the product rule, which we memorize using the mnemonic derivative of first times second equals derivative of the first times the second plus the first times derivative of the second. Now that we have derived the product rule, you, the viewer, are equipped to derive the so-called quotient rule. For the quotient q on x equals f on x divided by g on x, what is the derivative? The solution has the mnemonic derivative of the quotient equals derivative of the top times the bottom minus top times derivative of the bottom all over the bottom squared. With the other rules already explored in this slide deck, you can demonstrate this result, and so we will not spoil your pleasure in performing this derivation for yourself. Instead, we move to the final video in this slide deck where we calculate the derivative of sine.